Let me go ahead and start the recording here. All right, class. So we are working now we covered section 6.4, and people are comfortable with 6.5. 6.6 deals with applications to physics and engineering. How many of you are taking maybe Physics 1 or Physics 2 along with, or have to take it? Okay, Eric is. Esther, Michael. Okay, all right. So section 6.6 gives you a look into problems involving work that from a calculus perspective. So let me go ahead and bring up the ebook here. Section 6.6, applications to physics and engineering. That's where we are. So I want to give you a little guided tour of 6.6. One moment. Okay, so let me just see here. Okay, so the term work. What does work mean? Well, work is used in everyday language to mean the total amount of effort required to form a task. In physics, it has a technical meaning that depends on the idea of force. Okay, the idea of force. Intuitively, you can think of a force as describing a push or a pull on an object. Okay, for example, the horizontal push of a book across the table or downward pull of Earth's gravity on a ball. All right, in general, if an object moves along a straight line with some function, then the force of the object is defined by Newton's second law of motion. How many maybe have seen this formula in physics class? Force equals m times the second derivative of position. The second derivative of position, by the way, is what? What is the second derivative of position in physics? So the first derivative of position is velocity, and then the derivative of velocity is acceleration. So the second derivative of position is acceleration. So force, this formula 1 is that force equals mass times acceleration. Okay, and there are two units of force that we work with. Okay, one is force in newtons. Force can be given in newtons, but another unit of force is pounds. Okay, so weight, that's pounds. Okay, and that's a unit of force. So the way work is defined is it equals force times distance. So in order to do work on an object, you apply a force to the object, but the object has to move a certain distance. Okay, an object has to move a certain distance. If the object doesn't move a certain distance, you haven't done any work on it. Okay, so they give a few examples here. Now, they say, for instance, suppose you lift a 1.2 kilogram book off the floor to put it on a desk that is 7.7 meters high. Well, the force you exert is equal to the mass times g. G is acceleration due to gravity. Because in order to lift the book off the floor, you have to fight gravity. right? You have to do equivalent to what gravity's pulling the book down, but you're lifting it up. So to counteract gravity, you have to the acceleration due to gravity. You have to put in I'm going to say this the right way. The force that you are using to lift the book off the floor equals mass times the acceleration due to gravity. Force is mass times the acceleration due to gravity. Acceleration due to gravity is 9.8 meters per second squared. Okay, and you're multiplying that by 1.2 kilograms because that's the mass of the book. So the force that you applied is 11.6 newtons. Okay, so and then the work done would be equal to the force times the distance. So that's going to be the 11.6 newtons times 0.7 meters. And that equals 8.2 joules. How many maybe have seen these units in a physics class? Newtons for force, joules for work. Okay, so Michael's seen it, Eric has, Esther has, Tina has. Okay, so and if you haven't seen it, then if you do take a physics class, you will see it. All right. So now this is fine. You know, this is computing simple work. But you'll notice that the force is a constant force. The force is 11.76 newtons. So in this section 6.6, what we're going to do, and incidentally, I'll mention too, in the case where you have a 20-pound weight that's lifted 6 feet off the ground, the work to do that would just be simply the force times distance, but the pounds, the 20 pounds, is your force, okay? Because you have to overcome the 20 pounds to apply that force to lift the book. How many have seen, and then 20 times 6 would be 20 pounds times 6 feet. The work needed to lift this 20-pound weight 6 feet off the ground would be 120 foot-pounds. How many maybe have seen that in a physics or engineering class? Work in foot-pounds. Okay, Esther's seen it. Thank you, Esther. Eric has, okay. So the problems that you're going to see in WebAssign, all right, so Tina, it's the first time. Michael's aware of it. So in the problems that you're going to be doing in section 6.6, you're going to have problems where work is in foot-pounds and problem where work is in joules. Now, the key thing for when you have work in joules is that the distance has to be in terms of meters. Okay, so sometimes you have to convert things to meters in these problems. So this is a very simple example of work. Okay, but this is when force is constant. We want to allow now what happens if the force is a variable force. What if the force is not a constant force? So you suppose, well, to get a little bit, well, it's fine. Let's just look at the reading here. So let's suppose, and I'll highlight all of this here. Let's see here. Maybe I can put it in pink. Let me change it. Kind of like the pink. Okay. So that's good. Let's suppose that an object moves along the axis in the positive direction from x equals A to B. And at each point between A and B, there's a force that acts on the object. But the force, f of x, is a function of x. It's a function of where the object is between A and B. Okay, well, we can divide the interval up into n subintervals, each with equal with delta x. And we can choose a point in the ith subinterval, okay, point x sub I star, then the force at that point, f of xi star, that's our force. But if n is large, then delta x will be small. And if that, since our force is continuous, the values of the force don't change much over this small interval from x sub I sub 1 to x sub I. In other words, f is almost constant over the interval. So even though our force function f of x is changing with respect to x, if we look at the force over a small interval, okay, from A to B, that force is almost constant on that interval. So what you can do is you can approximate the work over the little subinterval as the force at xi star on the interval times delta x. So in other words, over that little subinterval, you're moving the object over the little subinterval. You're moving a particle, say, from x sub I1 to x sub I. You're moving it across that little distance with approximately the force f of xi star. Now they have a capital F. That's a typo. That should be a lowercase f of xi, lowercase f. But then you can approximate the total work by just adding up the pieces of work, separate little pieces of work along each subinterval. And of course, if you let n go to infinity, you're going to be taking smaller and smaller intervals, okay? And so the force over that interval, even though it varies, it's approximately constant if the interval is very small. So the work can be approximated by taking the sum of all these little work values over the interval from A to B. And so as n gets larger, the approximation will become better, and therefore we define the work done in moving an object from A to B as the limit of this quantity. And so here's the expression for the Riemann sum, or the limit of the Riemann sum, and that's equal to the work. So the work is equal to the integral from A to B of your force, your variable force with respect to x. Work equals the integral from A to B of your variable force with respect to x. And so you see with calculus, we're able now to compute the work that is done on an object for moving it to A to B when the force applied is a variable force. Okay, so this is where now we can do a more complex set of problems. Okay, because we're allowing for our force that we're applying now to be a variable force. Are there any questions so far? Are there any questions so far? Okay, well, let's look at a few examples here. So example 1, work done by a variable force. When a particle is located a distance x feet from the origin, with a force of x squared plus 2x pounds that's acting on it, how much work is done in moving it from x equals 1 to x equals 3? Well, using the definition then, and really, you know, this definition of work, it's really, I mean, they call it a definition, but it's the truth, right? It's the truth. I mean, we were able to show that the work is in fact equal to that integral. So that is what work is. So if you have a particle that's located, you know, in example 1, a distance of x feet from the origin, and you're applying a force of x squared plus 2x on it, that's a variable force, then the work done in moving the particle okay, from x equals 1 to x equals 3 feet is simply given here. Okay, it would be 50 thirds foot-pounds. 50 thirds foot-pounds. Okay. All right, pretty straightforward, but are there any questions so far? Okay, well, let's look at something with something called the Robert Hooke's law. How many have heard of Hooke's law? Maybe in high school physics or in the physics you're taking now. Hooke's law, H-O-O-K-E. Okay, Esther's heard of it. Thank you, Esther. Okay, and that's right, Tina. It relates to springs. It relates to springs. Hooke's law does. So let's look at Hooke's law. Okay, so Hooke's law. Okay. Hooke's law states that a force required to maintain a spring stretched x units beyond its natural length is proportional to x. So the force is equal to k times x, where k is a positive constant called the spring constant, and it depends on what on your spring. Okay, so this hopefully should make some sense to you. If you're going to stretch, how many have tried to stretch a spring before? Maybe like a slinky, or how many have like taken a spring and tried? All right, Justice has, Tina has, and Michael has. And how many of you have noticed that the more you try to stretch the spring, the harder it is. The greater the force you need to. I mean, if you stretch the spring further and further out, don't you need to apply a greater force? Okay. So Tina, Esther, Michael, and Rodrigo agree. Well, okay, and what is that force? Well, the force, based on Hooke's law, the force is proportional to the distance x that you're stretching the spring. And so intuitively, experimentally, you've tried that. Indeed, if you want to stretch the spring further and further, it's going to take a larger force. So force is equal to k times x. And the more x is, the more distance you're stretching the spring, that causes the force to be larger. So, they have a picture here, of course, of Hooke's law, and it makes perfect sense. Makes perfect sense. So work needed to stretch a spring. In example 2, they say suppose that a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. Okay, how much work is done? How much work is done in stretching the spring from 15 centimeters to 18 centimeters? Well, so according to Hooke's law, the force required to hold the spring stretched x meters beyond its natural length is equal to k times x. So if the spring stretched from 10 centimeters to 15 centimeters, okay, 10 centimeters to 15 centimeters, the amount stretched is 5 centimeters. But remember, you have to convert centimeters into meters, okay, because your work for this problem is going to be in terms of joules, but joules requires that your force is in newtons, but your distance is in meters. So you have to convert your centimeters to meters. And so then by Hooke's law, well, they're telling you that you're using 40 newtons, So 40 newtons is going to equal 0.05 times K. So what you have to do here to compute the work is you have to figure out your spring constant K. And so you'll determine that 0.05 times K is equal to 40, hence K equals 40 divided by 0.05, which is 800. Are there any questions so far up to this step here? Okay, let me make sure here. Hold on. All right, very good, Tina. Very good. People are comfortable. Okay. Well, then the force, since K equals 800, the force required is going to be 800 times X, and you compute the work. So the work would be the integral of 800x dx from 0.05 to 0.08. So again, you're going from 15 centimeters to 18 centimeters. Your starting value of x is 15 centimeters. I got to be careful. That isn't right. No, you're stretching the spring from 15 centimeters to 18 centimeters. Okay, but I want to say this the right way. When the spring is stretched at 15 centimeters, it's been, I want to say this the right way. Hold on. When you stretch the spring from 10 centimeters to 15 centimeters, okay, the amount stretched is 5 centimeters. Okay, and 5 centimeters equals in meters. It's I want to say this the right. It's 0.05 meters. So remember what you're doing here. Remember what you're doing. X is the meters, the amount of meters beyond the natural length that the spring is stretched. So, you know, you're starting out. Well, hold on a minute. I just want to make sure I'm explaining it the right way. So the natural length of the spring was 10 centimeters. But the spring, you start off with the spring being stretched to 15 centimeters. Well, 15 centimeters is 5 centimeters beyond 10 centimeters. So, or 0.05 meters, you know, beyond 10 centimeters. So that's why your starting value is 0.05. But then you're stretching the spring to 15 centimeters. Well, 15 centimeters, or 18 centimeters, I should say. Well, 18 centimeters is 8 centimeters beyond the natural stretch length of the spring, the natural length of 10 centimeters. So that's why you have 0.08 meters here. Right, so and then you just compute the integral and you get your answer. Are we okay? Are we on this so far? Okay, hold on. Let me get question. Hold on here. There's a block. It's Mr. Chen. What? Yes, question. I mean, are there any questions? Please let me know. So K justice represents your spring constant. So a spring, K will vary depending on the spring. Some springs are more rigid than other springs. So K is your spring constant. For this spring, we determined the spring constant to be equal to 800. And it's going to vary. It's going to vary depending on on the spring. All right, Justice, comfortable with that? All right, you're welcome. Are there any more questions regarding this problem? Okay, Mohammed's good. Mohammed's good. All right, all right. Well then, let me move on here to the next example, and then we're going to do a few. We're gonna do some on our own. I mean, I have some examples that I'm going to have you take notes on, but I want to just work a little bit with the book here. So example 3 deals with work needed to lift a cable. Take a moment to just look at that. Just take a moment to look at the example, and then we'll go over it. One moment. Okay. So I wanted you to read the wording a little bit before I started this problem. So here you have a 200-pound cable. It's 100 feet long and hangs vertically from the top of a tall building. How much work is required to lift the cable to the top of the building? So I think you can all imagine that if you were to have a 200-pound cable, it's 100 feet long, and it's hanging from the top of the building, and you wanted to pull that cable up, it would require work on your part. And of course, if you had a winch to do it, it would require work. So the question is, how do we compute this work? So in figure 2, in the figure here, you have the building. And the building is there's the cable. Okay, there's the cable. They're showing it hanging from the top of the building. And the idea here is we're going to take this cable and break it up into different little pieces of cable. So you see, the work needed to lift the entire cable up to the top of the building would be equivalent to the work needed to bring up each little piece of cable up to the top of the building separately. That's how you have to think of this. The work needed to lift the entire cable, the entire 100 feet of cable to the top of the building would be equivalent to taking that cable, breaking it up into equal pieces, and then bringing up each piece separately to the top of the building. So you're taking the cable and breaking it up into each into these pieces. Each piece is going to have a width delta x to it, and that piece of cable is a distance xi from the top of the building. So work is force times distance. So for this little piece of cable, let's just look at this little piece of cable in figure 2. This little piece of cable that's located xi, a distance xi feet below the building. So work is force times distance. So the distance we would need to bring that, the distance we required to bring that little piece of cable to the top of the building would be distance xi. But then the force needed to bring that little piece of cable to the top of the building would be equal to 2 times delta x. Okay, it would equal 2 times delta x. Now let's see if I can help make sense of this for you. All right, so let me go to the whiteboard. Let me go to the whiteboard here. All right, let me stop the sharing here. So we're looking at example 3. Looking at example 3. And I want to go to the whiteboard here. And all right, so the cable weighs 200 pounds. And there's 100 feet of cable. So what's the weight of the cable per foot? How much does this cable weigh per 1 foot? 2 pounds. That's right, everybody. That's right, Justice and Rodrigo. 2 pounds per foot. And what you're doing, of course, in the problem here, okay, is you have the cable. You have the cable. And you're looking at a piece of the cable that's delta x feet. Okay. And that piece of cable, to bring to the top of the building, you need to bring it up a distance of xi feet, or xi star feet. This, of course, will be on the recording. So the work to bring the ith piece, of cable piece of cable to the top. Okay, the work to bring the ith piece of cable to the top. Okay, I'll call that W sub I. Now work is equal to what? What is work equal to? How is work defined? Just simple work. Force times distance. Okay. So I need to find my F sub I times my D sub I. The force needed, I need to apply to this ith piece of rope times the distance needed to bring the ith piece of rope to the top. So what's D sub I going to be? We got to multiply two things. What's D sub I going to be based on the picture here? X. Right. That's right, Michael. X sub I feet. X sub I feet. Okay, so far so good. Let me know if you have any questions. All right, well now we got to find the force. Now we have to find the force. What are my units of force here? What are my units of force? Distance is in feet. Force is in, it wouldn't be newtons, right? The units of force are pounds. That's right, Rodrigo. That's right, Justice. So work's going to be in foot-pounds, but force has to be in terms of pounds. Now we have well, I mean, clearly we're bringing up delta X feet of cable. But I need to find the weight of delta X feet of cable. So, I mean, I don't have the weight yet. Weight has to be in pounds. How much would delta X feet of cable weigh? Well, I have to multiply delta X feet of cable by something. What would I multiply it by? How much would delta X feet of cable, this is a parentheses, how much would delta X feet of cable weigh? Okay, so your instincts are good. It's going to weigh 2 pounds per foot. So I have to put in 2 pounds per 1 foot. And so this then is going to equal, what happens to the feet over here? What happens to these feet? They say simplify out. That's right, Michael. So in other words, the weight of delta X feet of cable would be 2 times delta X pounds. And this is why you get then 2xi times delta x foot-pounds. I always like to bring in the units because when I have the units, it's telling me if the units are right, then it's a good indication that I'm doing the problem right. How many have used that kind of unit analysis maybe in chemistry? How many have used that in chemistry to help you know that, okay, Justice has, Tina has, so it's the same principle. Same principle. Esther has, absolutely. So the work needed to bring up the ith piece of cable to the top of the building, that piece of work is going to be equal, to 2 times xi delta x foot-pounds. That's the amount of work. Okay, are there any questions on that? All right, let me ask you a question here. So, we have this piece of cable here. We have it located there, and here's the here's the top of the building, right? There's top of the building there. If I were to pick out another piece of cable, maybe down here, of equal width, of course, equal width. Okay, here's another, gotta get this right. Here's another piece of cable right here. And, I'll call this piece of cable here cable piece 1, the one closer to the top. And I'll call the second piece of cable piece 2. Which piece of cable 1 or cable 2, cable piece 1 or cable piece 2, which piece is going to require more work to bring it to the top? The first piece of cable or the second piece of cable? Which is going to take more work to bring that? Which piece of cable piece 1 or cable piece 2 requires more work to bring to the top of the building? Both pieces of cable are delta x feet wide, by the way. So Justice thinks it's cable piece 2. Felicity says 2. Okay. Well, you're right. Why? Why are you saying 2? I mean, cable piece 1 and cable piece 2 have the same width. Why does it take more work for cable piece 2 to bring to the top of the building? That's right, Colombe. It's a further distance from the top. It's a further distance from the top. Okay. All right, and I guess, technically we want xi star here, but you get the idea. Are there any questions before we move on back to the problem?
Sorry, could you repeat the part, the difference between delta x and xi?
Between delta x and x, Tina?
Delta x, just x, and xi.
Well, x is they're using xi here because you see, xi. It's a good question. X sub I is gonna vary based on where your piece of cable is located. But you see what they're going to do. I mean, here's what they're going to do. Tina, are you comfortable with this expression here? That the work, needed to bring the ith piece of cable to the top is 2xi delta x. Are you comfortable with that? Because what we're going to do is we're going to make use of that. We're going to make use of that.
I guess that's why I'm asking the difference between delta x and x sub I.
X sub I is the distance that the ith piece of cable is from the top of the building, and delta x is the width of your ith piece of cable. That's what those mean.
Oh, okay. Thank you.
Okay, all right, you're welcome. Are there any other questions? All right, well, this is in the recording. Now let me go back to the book then. Okay, so now you understand where this comes from, what they're talking about here. The work done on the ith piece of the ith piece of cable to bring it to the top in foot-pounds is 2xi delta x. Well, then the total work done, okay, the total work done, hold on, I want to highlight that. I like highlighting it because it shows up then in the recording nicely. The total work done in bringing the entire cable to the top of the building would be adding up all these little individual pieces of work. Each individual piece of work is the work needed to bring the ith piece of cable to the top. You just add up all those individual pieces of work. But you let n go to infinity. Of course, your approximation is going to get better and better if you cut the cable up into tinier and tinier pieces, because over a tinier piece, the force acting on that piece of cable will be approximately constant, and the tinier the piece is, the better the better the approximation that force is going to be acting on that ith piece of cable. So the work is the limit as n goes to infinity, or I goes from 1 to n of 2xi delta x. And that becomes the integral from 0 to 100. After all, the top piece of cable, the distance there to bring that up is at x equals 0. The bottom piece of cable, well, that you have to bring that up 100 feet. And you got the rest of the cable in between. So the limits go from 0 to 100. So your answer is going to be 10,000 foot-pounds. Okay, are there any questions on that? All right, let me just see here. I'm checking one thing. I guess. How many think it's kind of cool? Pretty cool idea. Delta x is Felicity. Delta x doesn't equal 1. Delta x is the width of the ith piece of cable, and it gets smaller and smaller and smaller as you let n goes to infinity. I mean, this is a Riemann sum. This is what you're doing. You're using a Riemann sum to approximate the work, and you're letting n go to infinity. Delta x gets smaller and smaller and smaller. But you see here, the Riemann sum, in the highlighted part here with the work, the Riemann sum turns into the integral as n goes to infinity. That's what's going on there. All right. No, delta x won't be 1. We don't want it to be 1. We want it to get. We want it to be. We want the Riemann sum to turn into the integral. So delta x is like you remember your Riemann sums when you had like you add up the areas of the rectangles, and each rectangle has a width delta x, and you approximated the definite integral. It's the same principle, Felicity, the same exact principle. Same exact principle. Very good question. Excellent, excellent. And Tina, thank you, Felicity. Tina, I hope you're feeling a little better too with with so far. All right, all right. Well, let's see here. Let's go ahead. I think what I'd like to do. Let me just see. One moment here. One moment. Let's see. I think what I'd like to do is do now a problem dealing with pumping water out of a tank. Okay, I'd like to do problems like that. So give me one moment. I'm going to bring it up. One moment. Okay, so let me stop sharing here. Let me just bring in this this example here. So you've seen applications here of the integral in regards to work. You've seen an example where, where of course we're having a variable force applied to an object. So we saw several examples here. Work needed to stretch a spring, work on a variable force, work needed to lift a cable. Now what we want to do is a problem where work needed to empty a tank. The principle's the same. The principle's the same. As basically it's the same as the example where we needed to lift the cable. So let me give you a moment to copy this example down. Okay. All right, so take a moment to copy this example down in the picture, and we'll talk about it. Okay, all right. So in this problem, we have, hold on, we have a tank of water, tank full of water. Find the work to required to pump the water out of the spout. Use the fact that water weighs 62.5 pounds per cubic foot. Okay, so this is an interesting shaped tank. It's a triangular tank on the side. How many, incidentally, just out of curiosity, have thought, like when you see people emptying their pools, maybe you think, man, that must take a lot of work. That must take a lot of work to empty the water, to pump the water out of that pool. If you're, doing it from the top, like with a suction device or something. How many maybe have kind of thought that, or maybe like when you go to the gas station, you see a tanker and they're pumping water out of it. Well, you know what I mean. When how many are thinking that must take some work to remove that water from the tank? Has anybody ever thought that, or maybe not until now? Maybe if one person would say yes, I'll feel better. I don't like to think I'm the only person thinking of that. Not till now. Okay, all right. But all right. So the question is how are we going to solve this problem? How are we going to solve it? Okay, how are we going to solve it? So, well, again, what we could do is we could break the tank up into layers of water. We could break the tank up into layers of water. All right, and actually now, let me see here. I think I have my pages out of order, but that's okay. I can just go to, I got the right page here. All right, let me go to this picture here. I mean, they're not out of, when I scanned it, they were out of order, but now they're, So here's what we need to do. Here's what we need to do. So here's the tank. And what I want to do is I want to find the volume of the ith layer of water. You notice in the picture, I've delineated in black there a layer of water. And what we're going to be doing is to figure out how much work it takes to pump the water out of the tank. What we're going to do is we're going to take that water in the tank and break it up into layers. And we're going to find out how much work it requires to bring up each layer of water to the top of the tank. But in order to do that, each layer of water is going to have a different volume, right? Each layer of water is going to have a different volume. And that's going to affect the force needed to bring that ith layer of water to the top of the tank. So I have to be able to find an expression for the volume of the ith layer of water. But each ith layer of water is the shape of a brick, right? The shape of a brick or a parallelepiped. In other words, to find the ith layer of water, to find the volume, okay, I would need to find out the length times the width times the height for the ith layer of water. And the ith layer of water, again, that's this. Here's the ith layer of water. It's a brick. It's like I think of it the shape of a brick, or a box. A thin box of water. Thin box of water. I don't care whether it's a thin box or a fat box. In this case, it's very, very thin boxes of water, because what we're going to be doing is letting the width of that ith layer of water be delta x. But to find the volume of that ith layer of water, I need to do length times width times height. Length times width times height. Now, do we know what the length is? I mean, looking at the picture, can we fill in what the length is? Well, 12 feet, that's the part that's the part that's going to vary, Tina. The part that's going to vary is this part here. The ice layer of water, this part's going to vary. Okay. I guess I think of that as the length. I'll think of that as the length. The length is going to vary. Okay. The length is going to vary. So right now, the length, we don't know offhand we got to find an expression for that length. We don't know what that is. But do we know the width? Do we know the width? What's the width of the ice layer of water? 10. That's right. The width is 10. Good, Rodrigo. And what's the height? What's the height of the ice layer of water? Well, 6 is the height of the tank, but it's not the height of this. Again, what I'm doing is I'm talking about this sliver of water here, this ice layer of water here. What's the height of the ice layer of water? What's the height? Well, 6 minus xi, Kahindi, is the distance that ice layer of water is from the top of the tank. That's true. That's true. But I want to know what the height is. It's right there in front of your eyes. That's right. Almost right, Noah. It's just going to be delta x. That's the height. That's the height of your ice layer of water. Here, there it is, right there. And that height is delta x. So just like with the problem with the cable, we took the cable and broke it up into a bunch of little pieces of cable, each delta xy. We're doing the same thing here with the volume of water. We're taking all that water and we're breaking it up into layers of water. Each layer of water will be delta x high. So the question is now, how do we find the length? Well, what we have to do is we have to use similar triangles. We have to use similar triangles. Okay, so what I've done here in the picture, what I've done is I have the side of the tank here, the side of the tank, which is 12 feet long and 6 feet high. And then the ice layer of water, okay, well, let me just delineate this in red here. Gotta be a little bit careful. Okay, so the ice layer of water is a distance xi, feet from the top. But that means then it's 6 minus xi feet from the bottom. And what we want to do is we want to figure out this distance A here, because this distance A is my length for the ith layer of water. Well, by similar triangles, and I drew the two triangles there. By similar triangles, A divided by 6 minus I would have to equal 12 over 6. Because the similar triangles, the sides are in proportion. How many remember similar triangles from their geometry days? Okay, Justice remembers it. I hope you all would have seen that at some point. Well, all right, so I'm going to solve this for A. So A over 6 minus xi equals 2, and therefore A equals 2 times 6 minus I, and therefore A equals 12 minus 2xi. That's my length. That's the length L that I needed to find. Are there any questions? Are there any questions? Where did we get the 2? No, I just did 12. I just did 12 divided by 2. 12 divided by 6 and got 2. All right, are there any other questions? Well, now we can find the volume of the ith layer of water. Okay, we can find the volume of the ith layer of water, because the volume is, well, here. May I go to the next page? Are we good? All right. Oops, hold on. Hold on. One moment. Things. One moment. Just got to find it here. There we go. So the volume of the ith layer of water is going to be 10 times A times delta X. Well, A, we've solved it and found it's 12 minus 2xi. So the volume of the ith layer of water, well, it's 10 feet. Okay, that was our width times length, 12 minus 2xi feet, times the height, delta x feet, and that's going to give us 120 minus 20xi delta x cubic. Okay. So that's the volume of the ith layer of water. Naturally, the work needed to bring the ith layer of water to the top of the tank is going to depend on how far below that ith layer of water is to the top of the tank, but also it's going to depend on the volume of that ith layer of water. So now we're going to use the volume of the ith layer of water then to find the force on the ith layer of water. Because what we can do is we can take, I mean, what would the force be on the ith layer of water? What would the weight be? Okay, because remember, we're dealing in pounds, so force is the same as weight. Well, what we're going to do is we're going to take the volume of the ith layer of water and multiply it by the weight of the ith layer of water. Notice when we do that the cubic feet simplify out and we're left with pounds. So the force, F sub I, on the ith layer of water would be 120 minus 20xi times delta x times 62.5. That's going to give you 7,500 minus 1,250 xi times delta x pounds. That's what you're going to get. Are there any questions so far? Okay. You notice how I'm breaking the problem up in pieces. So like this wouldn't be until exam 3 that you saw something like this. But these kind of problems, you need to show this kind of work. I don't want to see just an answer because or just an integral. I mean, eventually we're going to get to an integral, but where's the integral come from? Okay, you have to justify that integral. So we're going to get there. What comes next? We know the force on the we know the weight of the ith layer of water. We know the ith layer of water is a distance xi feet from the top of the tank. What's the next natural thing to find? That's right. You know, the work needed to raise the ith layer of water to the top of the tank. Okay, so we're going to take the force. We're going to take that force F sub I, and we're going to multiply it by the distance d sub I, which is xi feet. And now we're going to get then 7,500 xi minus 1,250 xi squared times delta x foot-pounds. Okay, foot-pounds. Are there any questions on this so far? You have to ask if you're uncomfortable. You have to let me know. Okay, well, let's continue on then. Now we're ready to find the total work needed to lift the water to the top of the tank. And I'm talking all the water, right? All the water. Well, the work is equal to the limit as n goes to infinity of I equals 1 to n, the sum I equals 1 to n of w sub I. So we're adding up all the works, all the values of work, each to bring all these layers of water to the top of the tank. Okay, we're adding up all the values of the work, all these work values and each work value is to bring up the work needed to bring up the ith layer of water to the top of the tank, to raise it up to the top of the tank. Well, of course, the approximation will get better and better as we take more layers. So if we let n goes to infinity, we get then the integral. We get the work, and this is the exact value of the work. The work equals the integral from 0 to 6 of 7,500x minus 1,250x squared dx. And our limits go from 0 to 6 because we got water right at the top of the tank. That's a distance 0 from the top of the tank. And then we have water at all distances down to up down to the very bottom of the tank. Well, the water at the bottom of the tank is 6 feet from the tank. So the limits go from 0 to 6. Okay, are there any questions? Any questions at all? Well, not now for volume, you can have length times height times width, or length times width times height, or width times length times height. It doesn't matter. It all is volume. In this case, it's more convenient to have the width come last, or the height come last, because the height is that delta x value, and that's going to turn into dx when we take the limit of the Riemann sum. It turns into delta x. But yeah, it's fine. Very good question. Very good question. Are there any other good questions? Not Nell, you're comfortable with that? No. Well, yes, you thought we had to use 6 minus delta x for height, but that's not the case. We're using delta x for the height of the ith layer of water. Just like in the last problem, we used delta x for the width of the ith piece of rope or ith piece of cable. Same thing, same principle. All right, very good question, very good. Okay, well now let's get to our answer here, and here we go. So here's our work. And you just do your integration. The antiderivative would be 3,750x squared minus 1,253 x cubed. Limits going from 0 to 6. And you work it out. And you'll get 45,000 foot-pounds. Okay, take a moment to copy that down. All right, are there any more questions before we move on here? How many think this is pretty cool, being able to do this? How many think this is like a pretty cool application of integrals? Yeah, I agree, Mohammed. Pretty neat. How many are maybe a little bit nervous about it? Adriana thinks it's cool. I like that. I hope, I don't want you to be nervous, but you know. Okay, Sneg is sort of undecided. Adriana thinks it's cool. Mohammed thinks it's cool. Nina's a little nervous, but she likes the application. Okay. Felicity's cool. All right. All right, well, I'll tell you what I'd like to do is I'd like to give you some last time to practice the 6.6. The 6.6, there are two batches of exercises. The first batch, which is going to be due on Tuesday, along with your exam, that has 9 questions in it, and you ought to be able to do those. I'm going to probably talk a little bit more about section 6.6 in our next class, and just a little bit more. And but let's use this time for a little bit of classwork so that you can get. I'll feel good if you have some of that 6.6 assignment done, since it's due the same day as the exam. So let me put a stop on the recording here.